Let's talk about when 1,000 words are worth more than a picture or a table in the context of dealing with PDFs. So yeah, before we start, hello, my name is Caio. I work as a data scientist and a machine learning engineer here at Xebia as a consultant. So I've been working with AI since 2013. And from there, I've been dealing with many different contexts. So from embedding a neural network into a microcontroller in an electronic circuit, all the way to what I did in my master's and PhD, dealing with stroke patients with medical data, all the way to the industry nowadays, where so I work with Xebia. One of the efforts that we've been devoting to is what this talk is about. So the intersection is so we've been working with dealing with unstructured data and making it either structured or still leaving it unstructured, but in some pre-processed way. So yeah. Apart from that, I love music. I play the accordion, and I like hiking, and I'm very happy that the sun is up, so it's a good season to do so. So yeah. So let's start. Well, I'm gonna start. I cannot even call it a review. I'm gonna just gather in a minute or so, very quick review on RAG, just gather some concepts. And from there, I can address the semantical bottleneck from PDFs. Then we'll just define some premises on chunking, so I can work on top of those. So then I can share some insights on let's say, how to decompose tables in PDFs, and then discuss about the results of the impact of this kind of a technique or maybe this idea. It's too early to call it a technique, I would say, and see how it impacts retrieval in RAG. And from there, I would transfer all this rationale on how we would apply that towards images. So, okay, let's start. Well, RAG. So everything starts with a bunch of PDF files that we usually call a knowledge database, right? So yeah, let's talk about RAG in record time. From there, we get a PDF parser and transform those PDFs, convert into plain text. So now we have a jumbo big string we have to deal with, or many pieces of large strings from each document, right? What do we do with that? I don't know, maybe break it into smaller parts, what we call here chunks. So we do some chunking, right? And okay, now our problem looks like this. We have many tiny bits of strings. So, all right, let's keep going. So we feed those into an embedding model, and it's going to spit out some abstract representation of those pieces of text. So voila, we have now a vector database, right? So in this space, we have the equivalent of those pieces of text, but represented in some dimensions as numbers and as a point in the space. All right, don't think twice. Just build some user interface to have the user barfing whatever input they want to ask about those documents, and just catapult it in this raw form, let it fall in the vector space. Wherever it falls, just pick the top K documents, slap it into a prompt together with the user input, feed it to an LLM model, and let it answer the question, and voila, we have RAG. Cool, right? Or if you got annoyed by how simplistic I was, or even how condescending I was in here, you must have realized that it's a big no, or at least not exactly, right? There's more than that that we need to. There are more details we have to take into account, starting with the bottleneck of PDFs. So PDF stands for portable document format, and portable here means that we are able to see the very same document across many platforms and operational systems the exact same way. And this is something that we just take it for granted, and which comes at the expense of compromising semantics What I mean by that is like whatever arrangement we have of text structures, they're broken down into dummy shards of visual elements. So to every text, every flow of text, every well-defined structure, say of a table or column arrangement of text, they're all broken down into visual elements that have no semantic role anymore. This is optimal for just for the sake of visual fidelity. For the human eye, this is optimal. But losing that flow of information, this is something awful for computers to read a PDF file, right? So let's take this table, for example. Our eyes, our human instinct, makes us more inclined to go to like row-wise. Here, like reading A, B, C, D, E, F, G, H, J, and so on. But we could also, let's suppose this table makes sense if we go column-wise, we could go like A, G, K, B, D, H, L, and so on. So imagine this is so let's suppose this is rendered in a PDF file, and we give the same task to two PDF parsers. And look at that, from the same inputs, the same file, it takes different paths, right? One is going row-wise, as I said before, A, B, C, and the other one is going column-wise. So what is right, what is wrong? Huh? Not to mention how the PDF is even rendered to then serve as input for those readers, right? So this is a stream of a PDF file. And this would be, those would be what I said before, what I called before a dummy visual element, a dummy visual shard that is like something after this table is being broken down into. So this A would be this A, this B would be this B. So now you lose semantics for the sake of this very A is in this very position and so on. So there's a lot in here, right? How to traverse this stream, right? Which we see here different paths. How to even get from the semantical arrangement in some text editor to even render this. So how do we traverse at render time at when exporting a PDF? So you see it can become a rabbit hole, right? And also in here, so while before was preferred to go row-wise, now we see text arranged in columns. Now column-wise would be the preferred way. So we depend a lot on semantics, because if we always consider row-wise, we would have some parsed PDF into plain text with an output like, this is the first column of now, this is the same, an example document. It makes no sense, right? So we do need to take into account semantics. And like, as if this wasn't complex enough, in that simplistic view of RAG, we already take chunking into account right away, right? So, well, there's a lot to do before even going to chunking. And we have many, no matter how many tools, either simplistic or even sometimes useless techniques, right? If you've been having experiences and feeling pain with this sort of problem when crafting RAG applications, you must agree with me that there's no closed formula on some unique criterion on how to break down this big text into smaller chunks. So allow me to just to define some premises in here that we can work on top of when it comes to chunking. So then I can share some insights on how to decompose this kind of complex structure from PDFs. So the first premise here would be that the ideal chunk would be a very closed scope. It must be a unit of knowledge. So everything about that knowledge resides in a single scope in the most complete and independent way possible. Well, this premise alone could be too idealistic, right? Which takes us to the second and third. So the complexity of some sort of knowledge in whatever knowledge domain, it varies, right? some pieces, some knowledges that we acquire ourselves are more complex than others. So if the complexity varies, so will the chunk size, which is something that I define here, even our third premise. So if we have too big of a complexity and we still need to do chunking, then we need to break this bigger picture down to smaller chunks. So if the chunks are not completely independent, we must link every bit of every chunk to the complementary ones, so we can indeed bring them back together later on. So bear with me with these premises because we're going to revisit them later on. So yeah. Well, coming back to PDFs, to the bottleneck. So far, we saw that the strength of PDF is in its visual fidelity, right? So if some PDF is optimal for the human eye, for our vision, why don't we take this same vision-driven approach, right? I mean, current times allows us to use vision-based approaches with AI by using multimodal models. So quick show of hands of who's familiar here with the term multimodal model. Do we have hand raising in here? Or just say in the chat? Okay, let's do it in reaction. So yeah, let's react to the last message here. Okay, maybe this is oh yeah, reactions. So one is familiar with one. Okay, nice. So another show of hands of who is familiar with large language models. So now I think it's gonna pop a lot. Oh yeah, good. Amazing. So nice. So think of a multimodal model as a large language model. But it allows more formats of input. So to be processed in its raw form. What I mean by that is multimodal model can take text, but it can also take audio, it can take images, and so on, right? So before we just provided text to have an answer. Now we can provide, say, text to give some instructions and an image of the PDF itself. So now we have vision. So we have over the PDF file. So now we can see more in that PDF instead of mechanically converting it to text. So now we don't depend strictly on the PDF stream and all the what ifs about rendering the PDF. We don't even need to rely on that. Purely vision, right? So, oops. Okay. So yeah, and even for us humans, interpreting some sort of table can be challenging, right? I myself, when I read some complex documents, an equation or whatever, I normally take some side notes because later on, when I want to revisit this document, my side notes are descriptive enough, so it's easier and quicker to grasp the very concept from that table, that equation, whatever is in there. And this rationale is key to do some prompt engineering in here on how to make use of this multimodal model to have it like decomposing some sort of table. So, but using multimodal models in here is not something so novel. That's not innovation. So people have been doing that already. So, for example, they take a picture of the table from the document and they feed the picture and the text. So that's how we see that's when we see a multimodal model. It accepts text and image. And we say given this image, given this table, generate the same table, but in some LaTeX format, in some sort of syntax, right? And this can replicate, if this is LaTeX, right? So if we generate what this represents, we can get to the very table again. Or maybe generate some JSON, HTML, whatever. But those kind of approaches, they share a common denominator. They're too literal. I mean, don't get me wrong. If we throw whatever piece of code or syntax or structure, markup, things like this, right? I have no doubt that the LLM will be able to answer a question. Let's suppose this table makes sense and we ask a question and provide only this. It will figure out that this follows some sort of structure. It will understand, it will answer. The problem is, as we scale up an application, so R is a big pillar in here, which stands for retrieval. And when we have a lot of PDF files, we're not going to paste all of those into a single prompt to a model. We need to select, we need to filter the right chunks, right, to feed in here. So then we need to, and we measure those by similarity. So the inputs, whatever input that the user types, it must overlap, this is important, to whatever chunk, whatever piece of text we have here. So how will a very organic human question overlap with this? So the LLM can understand, but when we measure similarity to filter which chunks are important to include in the prompt, then we have no similarity. So LLMs are good at understanding this, but these kind of chunks, they must reach the prompt in the first place. So they will get blocked. So they'll get lost, and retrieval will never be able to retrieve, indeed, those kind of stuff. So let's take this use of multimodal models less literal. Instead of doing this reverse engineering, let's take it less literally. So I found this table in the internet, so I'm not biased on creating some example in here. So let's try to decompose this into their building blocks in a descriptive way, considering that kind of rationale to taking side notes, right? And I'm sure you're going to agree with me that let's suppose this table is interesting and we want to benefit from the contents of it. So let's say that the knowledge in tables, they reside in the values, whereas the headers, they only give shape to values, because we know they only give meaning to what 8 is about, 41 is about. But those are the knowledge, right? They just need some shape to make sense. So why don't we use prompts like explain? So we provide this as an image to the model, and we provide this prompt. So explain every cell in here, and tell me what that value, be it a text or a number, is about, considering the headers. So give format to whatever value you see in this table. And then some other instructions in case the LLM gets bored and tries to jump to some conclusion. I just say, don't jump to any conclusion. Just stick to what you see here and nothing more. And then I plugged these two inputs into even a model that is even deprecated now. And it spits out something like this. It's a very extensive list in here because every bullet in here is about a number. So this list goes on and on. So let's check the first one. So 150 is the number of students in the university group that answered question Q1A. Now I ask you, what else is in there about this very 150? Nothing, right? And as I mentioned before in the chunking, it must be a complete scope. So what else is there to talk about? 150, nothing. So everything about it is in this bullet. And now you see this is text, plain text, as the user would ask. If I say, oh, what is this? What does this 150 mean? I should expect another human replying just like this. So you see how now we're setting ourselves free from structure and how similar the question format is with respect to what we do want to retrieve indeed. There's a lot of similarity. I mean, it's a closed scope, but this 150, pretty boring. So let's find something else that is less boring here. Yeah, let's check this one out. So 73. So 73% of the students in the university group answered positively to question Q&A. See how it dances around and explores the space. And we can keep going. And here, 0.9 is the chi-squared value for the comparison. So we figured out two groups, university group and school group, for question Q&A, because a cell is merged. Look at the tiny details that the LLM was able to find and figure out the semantics, figure it out back. We're bringing back semantics, and everything here makes sense and describes in a very independent way some piece of knowledge. 0.9 is knowledge, but how do we shape it as knowledge so it makes sense in a complete scope like this? And then we can keep going for every other element in here. And then 150 again, but now it's this one. This one, question 1B. So then this list goes on for all the other questions, right? So we can see that each element in this list brings the full meaning of every number. So now we have indeed mapped in the very way that it would overlap with the user input. It figures out that there are comparisons, what columns have percentages, that is a statistical thing, right? So yeah, but how is this better, right? So allow me to introduce here an ad hoc analysis, because there's not yet a benchmark on decomposing tables. So the experiment that I carried out here was, let's suppose this table is interesting and someone minimally interested in this study and statistics, because this is about statistical comparisons. Someone minimally interested would ask questions like, is there some statistical significance between groups for this question? What is the biggest percentage point difference between some group in some category? Which questions show the most statistical significant difference between groups? How many degrees of freedom? Blah, 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 right? Pretty much down to earth questions and very human. So it's reasonable to say that humans would ask questions, would phrase questions like that. And the experiment is, I'm measuring the overlap between user inputs and the output of every strategy in here. So decomposition, the one that I just showed, that I just presented about the bullet point lists, very language-like descriptions of the numbers in the table, versus the overlap of those inputs with reverse engineering. As we saw before, it's just code, syntax, unstructured. And my goodness, the PDF parsing, as we saw in the beginning, that, I mean, do I go row-wise, column-wise, could be messy, right? So again, how it overlaps questions, each one of those, of course, against the chunks from all of those different formats. And for that, I'm using cosine similarity. And it's not very surprising that both the PDF parsing, that you could get everything messy, column, row-wise, whatever, and reverse engineering, when it comes to similarity, because like this is another important thing to point out. We're not throwing anything to the LLM to answer, because I'm pretty sure it will. But a requirement is those chunks must be retrieved. And for retrieval, we depend on higher similarity. So I'm stopping on the similarity. So yeah. So it's not very surprising that those two candidates, there's only so far they can go when it comes to similarity. So I would say that they're virtually tied. So in here, some cases cancel out each other. But you can see that decomposition is higher every time. I'm not even considering those values in here, because the vector space, I'm using embeddings from OpenAI, they're abstract, right? So we don't know what dimensions are about. So we cannot even evaluate by those numbers. So I'm just considering higher than relationship. And you can see that, I mean, of course, the decomposition would be higher because it's language, the similarity between language format in one text and language format in another text. Of course, it's going to be higher versus structure or messy text against organic question, right? So yeah, it's not very surprising that decomposition has a bigger overlap. And yeah, I already mentioned about that. So yeah, so what next, right? So we could see that it's promising enough to decompose and bring descriptive bits to paint the picture of complex structures just to retrieve. Then we can even use metadata on those chunks and refer to the material info, to the very table info. So yeah, so what next, right? So yeah, we can work, I mean, for today, this is another rabbit hole, but let me talk about images as we've been already talking about it. Images of tables, but images could be some technical schematic, could be tables as we saw, could be a diagram, right? Could be medical imaging, could be face, which involves some sort of anatomy, knowledge, could be landscape, right? So in here, let's talk about a diagram or yeah. And so how do we go from there? So maybe we could hard code some rationale in here about the category of images. So in here, we have some sort of step to assemble. So this looks like an assembly guide, right? So what we hard code in here is the rationale of a process. So we want steps, we want parts, we want actions, we want some description, right? So we can ask for that. We definitely enforce some output schema. And you might say, and then we get it all, right? We have Teflon tape, we have the wrench, flow meter, and how to assemble. And then you might say, like, yeah, but this has structure. This looks like reverse engineering. And you're right. The only difference here is that now this output is expected, there's some fixed format. There will always be those fields. Whereas in tables, reverse engineering is like there are many tables with with many different designs, different columns. So the output here varies. But in this case, we're hard coding a data structure. So with that, we can craft a code ourselves to go through these steps and glue them together to then form text. What I mean by that is like, oh, take one of this part, Teflon tape, and do whatever. Take another unit of wrench and do something. Take another one of flow meter and do something. So now we expect whatever piece of information that has been extracted from image, and you form the text, because in the end, you can still spit out text. And that's going to be independent, it's going to be descriptive, right? So this is something we can, this is just a middle step, intermediate step, so then we can craft the final text ourselves. Or also like some sort of medical context in here, right? What is this, like a CPR kind of a procedure? So we can hard code. I left those question marks because everything domain specific. We need some domain specialists to even describe the process, describe what needs to be hard coded. And then we can even ask questions like, what is that? What materials are used to do CPR for the respiratory trait? So then the LLM can bring back some sort of, all the objects in here and then actions. But in the objects, it's going to recognize this sort of a manual pump, part of my ignorance on medical field. So asking organic questions will overlap with whatever is in the picture. So you retrieve some sort of structured output. Again, you write code to go through this output and glue them together as text. And then the chunks are ready to add for questions like that, right? So what is the frequency? Maybe this should be combined with actual text in the PDF, but combined with this image, we have powerful chunks that would describe which items to use and which steps to take, what is the rhythm to manually pump for the patient to breathe, to do this ventilation, right? You can retrieve both the image and both text. Or even say some engineering context like how do I craft some sort of an amplifier so it would see regions here in the schematics and would bring descriptive text. So you got the gist of it, right? So it's basically about having an expected structure describing the only thing that is hard coded is some domain of knowledge in here. Of course, there's no general purpose way of describing all images. And even figure, this is a figure, not even an image, right? Because it's an illustration. And then from that point on, have text that overlaps with input. So I think that the biggest takeaway in here is we must make sure that the format of the user input overlaps as much as possible with how things are stored in a vector database. Most of cases are text. So let's bring image, audio, whatever piece of content into text very organically. There's a written question, so it must overlap with written text in language. So yeah, that was pretty much what I brought in here today. I wrote a blog about this experiment. I told the whole story. There's a GitHub repo. If you want to replicate the experiment, feel free to access the blog and read through it again, clone the repo. If you want to add a pull request and contribute, you're very welcome to do so. And this is my LinkedIn page. If you want to keep in touch, ask questions, I'm more than happy to answer them. Thanks.
Kaio, perhaps if there's anyone that has some questions for you right now, would you be able to answer them?
Yeah, of course.
Yeah. Anyone has a question for Kaio with regards to this topic we just had? No, seems pretty clear.
Oh, we
There's
have
one.
Yeah.
You can read it?
Yes. So okay. I would like to ask how we can use the results that we have obtained for an application. You mean from the graph that I showed? What kind of results? Okay. So the graph only says that out of those many, so when we're gonna craft some RAG application, it's nice that we use decomposition for complex structures instead of the simplistic way in the beginning of the presentation to just use a PDF parser. So the results in here is just to show how efficient, of course, in an ad hoc analysis, this use of multimodal models could be. So if you get a PDF, you can even use a parser to have text, but also use a multimodal model for every table to convert also those into text. So in the end, you have a lot of text, but everything now is informative and not messy as we would go through a table only using a PDF parser that you could have messy output. That's pretty much how we can benefit from the results. Yeah, sure. We have other questions. So how would you deal with a PDF that has both tables and text and images in there? That is a very good question. Well, this is the scope in here, but it's fine to talk about it. So maybe you can use regular expressions, for example, to filter what is table, what is text, right? So normally, or you could even use a multimodal model again. Maybe you can do a collage. Depends on how much you want to spend. Maybe you could make a collage of all the pages in a single image, and at each page you could put a page number, and say like bring back the pages where there is non-text elements. So be it a table, be it an image, and then and bring back in a list format. Then ask for some sort of syntax. So then page by page you could filter. So you're using vision to do a triage of what page needs to be treated as text only and what page needs to be treated as say to go through this sort of decomposition. So then you can know which page you just do more processing and use vision on it. Or you can even use regular expressions. I think that's another way to do it. Because, for example, especially in case of tables, so tables, usually those PDF parsers, when we go through a stream and convert it to text, maybe one header is glued to the next header to the next cell. So if you use the regex to see some word connected to a number, some word connected to another number, so those weird textual elements that don't look, so some typical patterns of what is not organic text. So you can use regex to spot pages where the text is messy. So when text is messy, it's pretty likely that there's going to be some sort of structure. So that's a simplistic, cheaper way to spot those pages that need special treatment.
Kaya, there was another question at the top. It says, which APIs are essential for this, or APIs are essential for this?
I mean, if you're going to use a third-party LLM or multimodal model, you can use the from those vendors, OpenAI, Google, those are the API calls to use multimodal models. So you send text and image, just so you use an LLM in code, it would be the same thing. Instead of just providing text, you provide text and the image with the same API calls. I also saw another question in here about not finding the GitHub link. Let me check myself for bringing this up. GitHub or repo. Oh. Okay, so it's in the text. It's in, where did I put it? in a flow, in a linear read, you can spot it, but okay, so if we go to the section where the graph is, I mentioned those three before the graph. I mentioned those three strategies. So decomposition, reverse engineering, and raw parsing. So those are links to the very code in the repo. If you click in one of those, you're going to find the repo, and then you can clone it. Oh, Lucy found it. Thanks, Lucy. Yeah. Nice. Any more questions?
Doesn't seem like it. Thanks, Kaio, and thanks everyone for joining. It was great. If there's anything else, and if you would like to know about any other information, I've put my email out there. You have Kaio's information as well. Please reach out to any of us. We'll be happy to help you.
Yeah, thank you. Thank you for nice session. Have a great day.